In this lecture, I'm illustrating how to do Hooke's Law, the lab related to Hooke's Law. So according to Hooke's Law, the force needed to extend a string is directly proportional to the extension, right? What I'm saying is, for example, according to Hooke's Law, if you have a spring here, and if you apply certain force right here, if you hang certain mass, force will be downward, that we call weight W, right? Then this displacement, it will displace. So initially this condition is said to be equilibrium when nothing is attached with this spring. After you attach this mass right here, it will displace with certain distance, right? Extension will be there. That extension that we can say X, suppose, right? This extension is directly proportional to the force. In this case, force is weight. Okay, so that's the Hooke's law. The force applied to stretch some string, some object, is directly proportional to the extension. That is how far this string goes from the equilibrium position. Okay, so once you click here, let me clear this window and go to the simulation window. And when you click on this one, this will lead to you to the simulation link. Let me go there. So this window, right? So right here there are several options. There are several options like introduction, vectors, energy, and a lab. So we are doing lab. That's why I'm clicking right here on the lab. There are several things you can see. Masses over here. You can adjust masses anywhere between 50 and 300 kilogram. And then spring constant, keep this thing constant. You don't have to change. Once you set it somewhere here, let it be here somewhere between small to the large, and don't move this cursor anymore, right? This should be constant. That means we are working for a particular spring. We are not changing the material of the spring. That is the meaning of keeping this constant. And click on this box that shows this equilibrium line so that you can measure how much is the displacement, then mass equilibrium, and you are done. So keep this one. If this number is other than this one, what is this number? This is the acceleration due to gravity here on the surface of the earth, right? Don't move here. If you move it here, it will be something different. So it will affect. What it affect? Mass will be, force will be different. If we keep this one, this is not down here on the surface of the earth, right? This is 30 is something else, which is acceleration due to gravity. So let me bring it back to the 9.8, exactly the value of acceleration due to gravity of the planet Earth, and keep it this one also constant 9.8. Okay, don't move anymore. Leave it this damping, and then you need to measure force and displacement. That's our goal. Let me go to the lab manual. If you scroll it down in your lab manual, here is a table, which is data table, table 1, right? And look at here, masses are given here. You can set these kinds of masses, starting from 50 to all the way down 300, right? I'm illustrating few data. Probably one data is enough because you can repeat same thing again and again by changing these masses. It's exactly same process after doing first line. So look at here. This is the mass. You can set in the lab simulation lab, and then stress X. How much stress is there? You can measure and write it down here. Then load in mass, kilogram. You can write down, here is the gram, right? You can convert this one into gram, just multiply, divide by 1,000, give you the kilogram, and then load in weight. If you multiply this value with 9.8, you will get load, which is weight, which is in Newton, and then stress X in meter. You measured initially in centimeter, and we have to convert it into meter because everything should be in SI system. Okay, let's go do experiment and get data. So let me graph this 50 kg because our first data should be 50, right? If you put it here, it will go up and down. Energy is changing all the time. You can look at here, but you don't need to worry about this plot because we are not taking any data related to kinetic and potential energy or total energy, whatever. So stop it. It will give you the displacement so that, you know, how can you measure the displacement? So initially, let me get it back again. Look at here. This is the equilibrium position, right? When you haven't attached this one, this mass, right? After you attach this one, it is displaced. It should be, right? Stop it. We don't need to record data when it is oscillating. We have to measure the constant distance, that is the displacement. Here is the ruler. Just grab it and bring it here and measure it from this line, right? Just to align this a ruler with this blue line. And how much is the displacement? Let me just get this side so that I can see this line, dotted black line. And I think it's 9.9. Let me make a guess because it's a 9.9 centimeter and half, right? It's here because this is the 10 big line and this one right here is 20. So it is 9.95. Okay, so this is 50 kg and X is 9.95. Okay, let me go to this and write down how much is the extension. 9.95 centimeter, right? And 50 gram. If I divide 50 gram by 1000, I will get 0.05, right? Which is in kg. Okay, so 0.05. 10 gone, 100. Yes, this is 0.05. Okay, so if you multiply this one by 9.21, let me write down data. Okay, you can multiply it and get the final results, but multiply it, which is 9.8, you will get the weight, right? What I did, this is the mass multiplied by acceleration due to gravity. You know, weight is equal to mg, right? M is mass in a kilogram and z is acceleration due to gravity. So you will get this weight. So you can also convert this one. This is in centimeter into meter. Let me write down, which is 0.0995. Okay, this is in meter. So you are done. So if you perform other data, if you choose second mass, which is 100 gram and 150 gram, 200 gram, 250 gram, and 300, how can you do that here? If you go to here, you can move this cursor and make it 100 gram, right? 100 gram. Right now it is 100 gram. Look at here, displacement is more, right? Displacement is more. If you make 150, let me bring it to the 150, which is our next data. Look at here, extension is more. The displacement from this equilibrium position of this spring is getting more and more when you move, change the mass, when you increase mass, right? It means the Hooke's law is verified. So if I move it more, increase more, look at here. Next data is 200. Let me make it 200. It is exactly 200, right? Right now, what is that? It is almost, it is becoming bigger and bigger. So let me bring this way. Look at here. It's almost 40, 41, 42, 43, right? Extension is 43 centimeter. If I increase again to 250, it's 250, and extension right now is 51, 52, 53, right? And if I make it like 300, extension is again increases to 62. In this way, what we saw from this experiment is if you increase the force on the spring, what happened is extension is increasing all the time linearly. That is, the force applied on the system, in this case, we have a spring, is proportional to the extension, that is displacement, which is F is directly proportional to X. Okay, let me write it down here. F directly proportional to uh, proportional to X, right? So this, in this way, we can prove Hooke's law. Okay, so in this way, you can repeat other data. Take data 100, 100, 150 as I did. You just measure it. The extension is already here, right? Just increase masses over here. You don't have to bring this ruler from here all the time. Just keep it here and take all the data. After you get data, this table is complete, full. Then you can make a plot, which is the x-axis here and y-axis here. So sorry, this is the not a straight line. Make it a straight line, x-axis and y-axis, right? Along the y-axis, put weight. This weight, I just represent it by n, and in this axis, put x. Okay, so if you plot this graph, you will get something linear plot, right? Because with increasing this weight, x is increasing. This is the relation, linear relationship. Okay, so after doing that, you can answer several other questions is given here. I think you will be able to look at the equation right here. Y equal to mx plus b. Okay, then what is b? B is the intercept, and m is the slope of the line that we obtained when we plot f and x. Okay, so read all these questions and answer all these questions. You can, if you know the mass, if you know the spring constant, from there you can calculate a spring constant, right? According to Hooke's law, Hooke's law is F is equal to Kx. Let me write it down here so that it will be clear. Actual Hooke's law is F equal to Kx. What is K here? K is the spring constant. That is, for this case, the spring we choose, we have to find the spring constant. Once you know F and X, you can find the spring constant. The slope of the line that you plotted is also give you the spring constant, right? So after you get a spring constant, you can find the unknown mass as well from by using the Hooke's law, right? Actually, extension is there. If you know this constraint, which is K, you can easily find the F. Once you know F, you already know F, G, right? That is acceleration due to gravity, 9.8. Then you can find the unknown mass, right? Here is the unknown mass. Look at here. If you, instead of this one, if you attach this mass, then you can find out more as well. Okay, so I hope you understand how to do this lab. That's all.